Kindly confirm. Have I shared the link? Let me test the microphone. Hello guys, you're welcome to Guide Academy, and in this tutorials you're going to have an exams prep problem to solve. So to cover different aspects of the applied electricity. Please, if this is the first time you're being on this channel, kindly subscribe and please don't forget to share to your friends. Okay, so we have our first question here. Our first question, it says that find the average and the RMS of the waveform shown here. So with this waveform, you are going to find the average as well as the root mean square value for this waveform, right? Okay, so you know that basically for you to find the average of any waveform, is simply first of all identifying the waveform, right? You identify the cycle. After identifying the cycle, let me write to find. You first identify the cycle, then after identifying the cycle, you identify your period, right? And after finding the period, you find the area of the cycle, then you divide it by the period. That gives you your average, as simple as that. So let's find the average of this. So you can see that this waveform here is not that regular, right? It's stepwise. So this one, we can extract what you call a step function. So for a step function, it has got different ranges for different um voltages here. So at voltage 2, you can see that it covers from this to this, right? It rose to voltage. I think we have voltage 6, and it also moved across a particular um range of time. Then it moved again to voltage 8. Then it also moved across a different range. So we will extract this as a function of time. So we have our voltage V, right? So solution, I'll say that my voltage V as a function of time is equal to a certain step function. Given the different ranges, I'll have 2 for 0 is greater than or equal to t, less than or equal to 5 seconds. So you can clearly see that from 0 to 5 seconds, we have our waveform as what 2. It's clearly here. Then the next is 6, right? So 6 from 5 to 10. So from 5 to 10, we have 6. So we're going to have 6 here for 5 less than or equal to t less than or equal to 10 seconds. Then from there, you move towards 8, right? So I'll have 8 for 10 is less than or equal to t less than or equal to 20 seconds, like that. Therefore, this is my cycle. This is my cycle. The same thing happens from 25 to 40. So you're not going to repeat. You identify just a single cycle. So having identified my cycle, the next thing is for me to identify the period for this cycle. So period is where it's starting and where it's going to start again. So it started from 0 and it's going to start from what? 20, right? So this is it. So we are having the starting point here and another starting point here. So it is our period T is simply equal to 20 minus what? 0, which is 20 seconds. At this point, we just have to find the area of our cycle. Then we simply divide it by period and we are done finding our average. But to find the area of our cycle, we are to use the integration method, right? So I'll have my general average to be equal to 1 out of 20. That is my period dividing the whole area, right? And since this is a stepwise function, what you're going to do is we are simply going to integrate with respect to the interval. So I'll first have my um, definite integral, okay? For the first function, I'll have my definite integral from 0 to 5 to the t, plus my second one, I'll have integral from 5 to 10, 6 dt, plus integral from 10 to 20, 8 dt, close bracket. So once I integrate this over their respective regions, because this our function is not uniform over, the entire regions, it has got different values. That's why we call it stepwise function, and we treat it independently. So at this point, this is a very simple integration, and I'm going to have 1 out of 20. Integral respect to 2 dt is going to give us 2t, right? So I have 2t 0 to 5 plus 60. I have 5 to 10 plus 8t. I'll have 10 to 20. Then you can evaluate this even using a calculator. What are you getting? 5 will give us 10, 0, right? So 10 plus 10 goes here, 60 minus 30, that is 30. Then you have plus 20, which will give us 160 minus what, 80, right? And that is 80. What are we getting? 10 plus 30 is 40, plus 80 is 120. 120. So I'll have 120 out of 20, and the answer is 6 volts. So the average voltage for this waveform is simply 6 voltage. Now let's quickly do that of the root mean square value. So for the root mean square value is similar. The only difference between the average and the root mean square value is that you square your cycle before we find the area. So we simply find the area of the squared cycle. So the formula remains, and also we find the square root of the entire thing. I'll have 1 out of 20. Similarly, everything will be under the square root sign because you find the root mean squared. So 1 out of 20 multiplying. Now my function becomes integral from 0 to 5, right? But it becomes 4, not 2. So 4 dt plus integral from 5 to 10, 36 dt plus integral from 10 to 20, 64 dt. That's all. So all this evaluated under the square root sign gives us our RMS value. So I still have this. Let me continue evaluation. So 1 out of 20. Then I'll have here, I'll get 4t 0 to 5 plus 3060 5 to 10 plus 64t from 10 to 20, right? So this gives me 1 out of 20 out. Then 40, I'll get 20 plus 36, 360 minus 180. That is 180, right? Plus 6. So 64 times 20 is what? 1280 minus 640. So it's apparently 640, right? So you simply have 20, 200, 840, right? So 1 out of 20 times 840, everything under the square root sign. So this cancel this, you get what? 42, right? So square root of 42 was the answer. Square root of 42. We enter 42. And that is 6.48 volts. 6.48 volts. So you can see the difference between the average and the RMS value. The RMS value give us a strong value representing our AC more than the average, right? So this is how you solve such a problem. And this is some kind of an unusual waveform you would meet. Now let's move to our second problem. But before then, if you haven't subscribed to this channel, please do well to subscribe so that you get notified with content. So this is my second problem, which I'm going to take you through, and it says if an ammeter is connected between the terminals A and B of the figure shown below, it reads 10 milliamperes. If a 10 kilo ohm load is connected across the terminals, the load current is 6 milliamperes. Find the current in a 15 kilo ohm load. So let's solve this problem nicely here and extract the information. So we've been given a linear network without any resistance given, without anything. It's just a black box, right? All that you've been given is this is a linear network, and you have terminals A and B. And you are saying that if this terminals here is connected across an ammeter, it reads 10 milliamperes. But if I introduce a 10 kilo ohm load here, it's going to read, when I introduce a 10 kilo ohm load, it reads 6 milliamperes. Where is it? Yeah, so 6 milliamperes for 10 kilo ohm. Yes. Find the current in a 15 kilo ohm load. So this is a problem we've been asked to solve. So for the first start, you realize that when there was nothing connected, I had 10 milliamperes. But for 10 kilo ohm load, it gave me 6 milliamps, and I'm looking for 15 kilo ohm load. So what do you think this problem will be about? I mean, what application are we looking at? So this is simply an application of Norton's theorem, right? So Norton's theorem says that if you want to find the current through a particular resistor, you have to first take that resistor out and introduce an a short circuit current, right? So here we assume that because we don't know what the linear network is, but these two networks here, these two terminals here, there is nothing. So far as we've not connected any load, once we introduce our ammeter, we are just um measuring the, let's say, short circuit current, right? So we introduce this as our IN. So our IN is simply the 10 milliamps. So that was a reading when the terminal C and B was connected between the ammeter. Now for the 10k ohm, it's a special resistor R which was introduced. So R was 10k ohm, and you realize that we got the current through this R to be 6 milliamps, right? But in this case, what is missing? We weren't given Rn, that is the load originally connected. That is what is missing here. Once we get our Rn, then we can find the corresponding current that will be measured between the 15 kilo ohm load. So let's find our Rn. But before that, you know that the Norton's equivalent circuit, we say that we have our In as our source here, right? We should go into our Rn in parallel with the resistor you want to find the current through, right? So if I want to find the current through this resistor I, we use the inverse, right? Which we call the current division rule. So I'm going to have my Rn over my Rn plus my R times my In. That gives me the current through the resistor. I'll apply the same thing here. Now I don't know my Rn, but I know my R, which was what, 10 kilo ohm. So my Rn over Rn plus 10k times my um current, Norton's current is what, 10 milliamperes, right? So 10 mils. Let me throw the milliamperes and the kilo somewhere, right? And maintain the 10. It should be equal to my I, and the I was 6. So doing simple algebraic expression, you have our Rn times 10, right? So 10 Rn, then all over Rn plus 10 is equal to 6. When I cross multiply, I get 10 Rn is equal to 6 Rn plus 60. Subtract and I get 4 Rn is equal to 60. My Rn is simply equal to 15 kilo ohms. So now I've seen that my initial, which is my Norton's resistance, is what, 15 kilo ohm. And the question is asking us to find the current that will be measured across a 15k load. So it's so simple. Right now we know that our R is simply 15k ohm. Our Rn, which was calculated, is also equal to 15k ohm. We know our In already to be equal to 10 milliamperes. Then what is our I? Our I is simply equal to our Rn, 15 over 15 plus 15 times what, 10. That is giving us 1 out of 2 times 10, simply giving us 5 milliamps as our answer. So the current reading within the 15 kilo ohm load will be 5 milliamperes. This is all for this particular problem. And if you haven't still subscribed, please do what, subscribe, support, and share to friends whom you think they will find it very helpful. Our third problem. So a coil of 4,000 turns carrying a current of 0.05 amperes is wound on part A. So we have the figure here. The length and cross-sectional area of part A are 0.2 meters and 1 meter squared respectively. The length of each air gap is 0.05 meters. The relative permeability of part A is 500. Here are the options. It says A. Find the combined reluctance of part A and the air gaps. B. Given that the magnetomotive force drop in part B is 80 ampere turns, calculate the flux in milliweber in the circuit. C. The flux density in a material A in a circuit is 1 milliweber per meter squared. Find the flux density in a material of the same dimension but with a relative permeability which is twice that of A when replaces A in circuit. So this is a very beautiful problem and let's break it down and solve it. So we need to identify our parameters. So the coil is having 4,000 turns. That's our first keyword, right? And carrying a current of 0.05 amperes here. Is wound around part A. So meaning that this part A here, we have this coil. So I can introduce the coil somewhere here, right? And introduce the current here, which is I is equal to 0.05 amps. Now, you're saying that it is 4,000 turns. So our N is equal to 4,000, right? Good. The length and cross-sectional area of part A. So our LA equal to 0.2 meters and our AA, right? A sub A is equal to 1 meter squared. Then the length of the air gaps. So the air gaps introduced here is 0. So length G of air gaps is 0.05 meters. And the relative permeability of the entire A, material A, is what? 500. So we have to find the combined reluctance of part A. So given the parameters of part A, again, so let me write the solution here. So to solve this, we need the parameters of part A. LA is given as 0.2 meters. The area across, which is uniformly distributed, is 1 meter squared. The length of the air gap is simply equal to 0.05 meters, right? And obviously the area of the air gap will also be got 1 meter squared because it's a uniformly it has, so as you can see, so to find the combined reluctance of part A and the air gaps, what's the reluctance formula? You know that generally reluctance is equal to the length of a section divided by the permeability, relative permeability times permeability of free space times our area, right? So once you have this as our general formula, you know that if it is air gap or free space, meaning that our mu zero will become sort the only thing. We wouldn't have relative permeability. So now since you are finding the reluctance of both parts A and the air gaps, what do we mean? We want to find that of LA over UR times mu naught times A of the part A plus L of the air gaps over, now is mu naught alone. We don't have relative permeability for air gaps, right? So times our area for the air gaps. But since the air gaps are 2, we can just multiply 2 by this, the same dimension, and that is all. So this one is simply introduce your LA is 0.2 over, we're giving the relative permeability to be 500 here. Okay, so we just write 500 here times 4 pi times 10 to the power negative 7. Just keep this in mind. The permeability of free space is 4 pi times 10 to the power negative 7 times the area, which is 1 meter squared, plus 2 times the length of the air gap 0.05 all over mu naught 4 pi times 10 to the power negative 7 times the area, which is also 1 meter squared. Then this answer becomes solution for the first one. So just enter this into the calculator. 0.2 over 500 times 4 pi times 10 to the power negative 7 plus 2 times. So 2 times the 0.05, you can simply make it 0.1. Okay, make things either 0.1 over 4 pi times 10 to the power negative 7 So the answer here is 79895.781, and we are getting the unit. So this is reluctance, right? The unit is, sorry, the unit is ampere per Weber, right? So you are supposed to get this. Please, if you're not getting this, then you have made a mistake with any of the units. Now let's go to the B part. It says that given that the MMF drop in part B is 80 ampere turn. So you go back to the diagram, you realize that we didn't get any information about part B. Part B here, we don't know the length, we don't know the area, but actually the area is uniform, so we don't know the length, right? So if you want to find, it's the question says you should calculate the flux in in milliweber in the circuit. So we actually need the flux in the circuit, not necessarily the flux in B, but we've been given the MMF drop. So in magnetic circuits, we follow similar Kirchhoff's rules, right? But just that here we see that the sum of our magnetic field intensity across the respective lengths within the circuit should be equal to the total magnetomotive force within the circuit, right? So here what we do is you will first, we know that the drop across B is 80. Then what is the drop across A? That is should be the point of view. But initially we're given that the coil is having 4,000 turns, carrying a current of 0.05 amperes. We can find actually the total MMF from that end. Remember that F is equal to Ni, and this gives us the total MMF in the circuit. And we know that our N is 4,000. We know that our I is 0.05 amps, right? Multiply this, you are going to get 280, or you can say A for short, right? Now, this is the total produced in the circuit. And out of this total, we are having 80, like 80 ampere turns being induced here or dropped across the B. Therefore, if you want to find the flux, we need to know the reluctance. So let's see something here. Right now, we need a flux. Another formula says that F is equal to our flux times what? Our reluctance. Is that not it? So to find the flux is simply equal to F over what? Reluctance. But where do we know the reluctance? We only know the reluctance for the part A, including the air gaps. Therefore, we need to find the particular MMF across the A alone before we can find our flux. Since the drop across the B is 80 ampere turn, then we can subtract it from 200 and we get a drop of 120, right? So our FA plus air gaps is equal to 200, and it's here. So we have 280 minus 80. That gives us 120. So the 180 is the MMF across our A part, right? The section A, including the air gaps. The reason why I've added the air gaps is we have the combined reluctance of the air gaps in part A already. If I had gotten the reluctance only for part A, fine, you could have also used that, right? So let's see something. But let's see. We can't actually use that per se. Now, the truth is, when we come to this diagram, in magnetic circuits, an empty space is also considered as part of the circuit. So we have three sections: A, air gaps, and B. Therefore, we need to get the reluctances of the flux in A, in the air gaps, and this. Similarly, we have to find the MMF drop in the air gaps in A and B. But since we know the drop in B, meaning that the remaining drop will be for the air gaps and A, that is why we have to combine them. Therefore, since I know that my F is 120, therefore my flux, sorry, the flux is equal. That one, take note. The magnetic flux produced is equal. It moves around the circuit of equal, so far as they're in series, it's equal, right? It's equal. So whatever we find becomes the flux in the entire circuit. So we get 120 over the answer we had here, right? Which is 79895.781. So we put that into the calculator. We get 79895.781 divided by, sorry, it's actually 120 over 79895.781. So this gives the answer 1.502 milliweber. So 1.502 milliweber is the total magnetic flux in the circuit. Let's check the third question. It says that I think the third question is slightly isolated. So it's saying the flux density in a material A, right, in a circuit is 1 milliweber per meter squared. Find the flux density in a material of the same dimension, but so we are interested in the same dimension, but